Hello everyone, I'm Deng from the Southern University of Science and Technology. Today I will introduce our work CipherH, automated detection of ciphertext channel vulnerabilities in cryptographic implementations. This is a joint work with Dr. Mengyuan Li, Yining Tang, Dr. Shuai Wang, Dr. Shoumeng, and my supervisor, Dr. Yinqian Zhang. Okay. TE is the hardware extensions in modern processors which provide software applications with confidentiality and integrity. At present, many cloud computing companies are using TEs, such as Microsoft, AWS, and Google Cloud. However, TE is not silver bullet, and recent studies have suggested that it still faces many security threats, and we divided them into the following 6 categories. Among these attacks, the most notorious one is the side-channel attack. Traditional side-channel attacks include cache-based attacks, DRAM-based attacks, and so on. Now, in this work, we focus on a new type of side-channel, named Ciphertext side-channel, which is the emerging threat toward TEs. The Ciphertext side-channel was first illustrated in 2021 and was extended in 2022. Okay, now the question is, what leads to the Ciphertext side channels? In order to answer the question, let's first see the hardware memory encryption used in TEs. For TE, the memory encryption mode used is constrained by 2 factors. At first, in order to support random memory access efficiently, chaining mode cannot be used. Secondly, flash mode is also not suitable, since additional space and latency are needed to maintain the counters. As a result, TEs such as AMD SEV has used AES encryption with XES mode. To be more specific, memory is encrypted per 128-bit block. Besides, in order to avoid inferring plaintext via the same ciphertext, a twink function is also introduced. However, without freshness, the same plaintext at the same address is encrypted into identical ciphertext. Such design choice leads to the notorious Ciphertext side channels. At present, Ciphertext side channels exist in TEs with deterministic encryption, such as AMD SEV, Intel TDX, and ARM-CCA. Okay, now let's see how an attacker can infer relations of key bits by Ciphertext side channels. Consider this cryptographic program, and there are 2 memory writes towards the same variable A. The first one writes A with key 1. Key 1 is the first key bit of a secret key. And the second writes A with key 2. Key 2 is the second bit of the same key. Now, the attacker can cite 2 observations after each memory write. And if the attacker observes that the ciphertext changes, he can infer that key 1 is not equal to key 2. Otherwise, he can infer that key 1 is equal to key 2. In order to defend against the Ciphertext side channels, one possible way is to fix it from hardware level, such as changing the memory encryption mode. However, it will introduce too much performance overhead. On the contrary, software-level mitigation is more feasible, and AMD has released a white paper to guide software developers in defending against Ciphertext side channels. As such, in our work, we propose CipherH, which is a vulnerability detector to locate Ciphertext side channels in the program. At first, we model Ciphertext side channels. We give 2 conditions that it should satisfy. The first one is that there are 2 sequential memory writes, and the second is that these 2 operations are secretly dependent. Then we use formula W1 and W2 to denote 2 writes, and key 1 and key 2 to denote 2 secrets. Then the written values can be expressed as W1 key 1 and W2 key 2. Next, we can get safe scenarios. Scenario 1 means that no matter what values key1 and key2 takes, the ciphertext keeps unchanged. At the same time, the scenario 2 means that no matter what values the key1 and key2 takes, the ciphertext always changes. And when neither of these two cases are satisfied, we underline that the information leakage occurs, which means that the changes of ciphertext depend on the secret key. And the information leakage scenario model two different executions following the same path. And during one execution, the second memory write changes the ciphertext, and during the other execution, it returns the ciphertext. Okay, next, let's see our design. Our design includes two parts, dynamic taint analysis and static symbolic execution. In our dynamic taint analysis, we taint a secret in the program, and our taint propagation is based on the data flow synthesizer. We also pick the function parameters, return value, and memory load as the taint sink. The output of this step is the set of tainted function, which is also the input of the next step. Our symbolic analysis includes intra-procedure analysis and inter-procedure analysis. In intra-procedure analysis, we maintain two lookup tables. And if a constraint solver answers yes, it means that we have successfully identified vulnerabilities. And the CipherH will output to memory write address and a pair of secrets. For inter-procedure analysis, consider the huge cost of inter-procedure symbolic execution. We use pattern-based analysis. We give two patterns. Pattern 1 means that a function f is called in a for loop. And the second pattern means that at least one parameter of f is tainted. These two patterns are from the observations of cryptographic libraries. Okay, let's see our result. In total, CipherH can cover more than 2,000 functions. Among them, more than 300 are tainted. CipherH has reported 83 intra-procedure vulnerabilities, and we have validated all of them. Besides, CipherH can report 153 inter-procedure vulnerabilities, and we confirm that most of them are true positives. Besides, CipherH also reports a vulnerable patch in WolfSSL. And more details about the vulnerability could be found in our paper. We also compare CipherH with other side-channel detectors, such as Empirical's catch-as and catch-audit. And the result shows that none of them are scalable to analyze our test case. We also want to see whether the patterns we picked will affect the vulnerabilities. And the result shows that these two patterns we pick are enough for scalability with low false positive rates. And last, we want to see that how compiler optimizations will affect the vulnerabilities. And the result shows that aggressive optimization, such as O2 and O3, tends to place variables into a register. As a result, there are less memory writes in the program and thus less vulnerabilities. Okay, let's make a conclusion. In this work, we propose CipherH, which is for the first time formulates the ciphertext channel, and it also can identify ciphertext channel vulnerabilities in production software. However, CipherH may produce false positives. It's mainly from the inter-procedure analysis we used, and false negatives mainly from the dynamic taint analysis we used. In the future work, we can develop some tools to eliminate the vulnerabilities found by CipherH. Okay, this is our code and our paper. If you have any questions, please feel free to ask me by this email. Okay, that's all. Thanks.